In this video, we're going to focus in on a new type of reaction. Previously, we had talked about several other types, okay, but this specific one, called a redox reaction, okay, is one that's very prevalent in chemistry, and it's usually something that older students in high school deal with, but we just want to touch on it and learn how to deal with it on a very simple and basic level, okay? Redox reactions focus on electrons and charge instead of atoms, okay? So in previous reactions we've done, atoms have switched places and moved around and created new compounds. In this one, electrons on metals generally are going to be flip-flopped to change their charges, okay? So these reactions are only going to deal with electrons for the most part. So the key here is to know that electrons are what drive redox reactions, okay? So let's take, for an example, we have some copper in solution, so it's in water, okay? So it's an ion, it's floating around in water, all right? And we put some iron metal in there, okay? Well, potentially, the copper, which is missing 2 electrons, right? It's a positive ion, all right, is going to want to take some electrons from this iron metal. Iron has lots of electrons. Why not share a few? So iron will say, okay, I actually want to be charged anyway. So I'll give you some of my electrons, and copper, you can have them. So iron will take some of its electrons, give them to copper, and when it does that, copper will become a metal, and it'll have a charge state of 0, right? It'll be neutral. And then iron will be missing 2 electrons, and so it'll become Fe2+, an ion in its own right. Okay? That is a redox reaction. It is when 2 metals give each other electrons and change their charges. Okay? Notice, okay, I have these charges circled on the metals. Okay? When we talk about redox reactions, we call the charges oxidation states. Metals can have multiple oxidation states. For instance, copper can be copper 1, copper 2, and iron can be 2 and 3. So they have multiple oxidation states. You have to be able to tell which kind you're making and which kind is going to come around. So oxidation states are important. We just call them that instead of being called charges at this point when we're talking about redox reactions. Okay. The metal in a redox reaction with its charge decreased, so in this case it would be copper, is called the reduced metal. Okay? And it's called the reduced metal, and it's also called the oxidizing agent. And that's because the metal with an increased charge is oxidized, and that metal is the reducing agent. So they're working together to reduce and oxidize each other. Notice it's called a redox reaction because if you take this section right here and this section right here, it spells redox. Okay, it's not just some random name. We got it from other words that are associated with it. Okay. Here are some examples I have, some basic ones. Okay. So I've got iron 3+, and it's going to react with some neutral zinc. Okay. Zinc, when it's an ion, it only has 1 oxidation state, and it is 2. Okay? So zinc is going to become 2+. Alright? And iron can't go down to 1, so it has to go to 0. Okay? So it's going to become a neutral metal. Notice the number of electrons don't match up. Okay? 3 electrons are moving here, but there's an extra one lying around. So what that means we need to do is we need to find multiples of these to make them balanced charge-wise. Okay, so if I put a 2 in front of the Fe, a 3 in front of the zinc, a 3 in front of this zinc, and a 2 in front of here, you'll end up having the same number of irons, the same number of zincs, and the electrons will match up, 6 and 6. Okay? That's the goal. All right? Here's our next example. We've got cobalt 2+ reacting with manganese plus 6. Okay, so when we do that, we're going to end up getting cobalt on this side and manganese on this side. Cobalt is going to be the oxidized metal. It's going to go up to +4. Manganese is going to go down Manganese is one of the coolest metals around. It has the most oxidation states. So it's going to go down just to +4. Okay? So when it does that, this one's being oxidized, this one's being reduced, and because the number of electrons that are being exchanged are the same, we don't have to put numbers in front of the metals. Finally, in this example, I don't have just the metals in there, I have their respective compound anions with them, okay, oxygen and sulfur. And so in this one, we have to figure out what the charges of the metals are. Okay? And that's pretty easy to do. Oxygen, as we know, is a -2 ion, and there's 2 of them, so that means there's -4 total over here. That means that this tin, this one tin over here, has to be +4 because compounds are neutral. So we know that Sn is +4. Over here, sulfur is -2, and there's 1 iron, so that iron must be a +2 charge. That means that this one must be the one being reduced. Okay? Tin can go from 4 to 2, so we'll have tin come over here. And it's going to be paired with an iron that is going to increase because something has to be oxidized. And as you notice, we're going to hop up. We're going to be missing 1 electron here, right? There's 2 electrons going away, but only 1 over here. So we're going to need to double up how much iron we have. Okay. To finish off, we just need to put their respective things together. So we'll put S over here. So we have tin sulfide. And then we're going to have to put oxygen with iron. And since there are 6 total charges here, we're going to have to put 3 oxygens over there. Okay, that means there's 6 oxygens here. So to balance it out, we'll have to do a 3 and a 2. Alright, so it didn't quite work out right. Okay, sometimes these problems do, and when this happens, you just have to use some trial and error to balance the equation. Okay? Remember, you need to have the same equal number of metals and charges, so it'll take a long time for me to balance this, so I'll just leave it like that. But just know that this is not done. You would still have to make sure that it all balances out. Okay? So remember, redox reactions are throwing a new thing at you. We're trying to balance the charges of the reactants and the products. We're just changing electrons around. That's what redox reactions are so different.